Before a single 5G tower ever goes up, before a single cable gets laid in the ground, our entire wireless world gets built in a hidden, virtual space. Today, we're going to pull back the curtain on that invisible blueprint and see exactly how these lightning-fast networks are actually born. We've all been there, haven't we? You're on a super important video call, you're walking through a busy downtown area, and bam, the screen freezes. You're doing that awkward dance, holding your phone up to the sky, just trying to find that one little spot where the signal comes back. So why? With all this amazing technology, why is a perfect connection still so hard to find? Well, it's because our wireless environment isn't some big empty space. Oh no. It's more like a chaotic, invisible battlefield. You've got radio waves bouncing off buildings, fighting each other for bandwidth, and trying to navigate this jungle of physical stuff. It's an unbelievably complex web, and engineers have this massive task of trying to bring some order to all that chaos. And that really gets us to the heart of the problem, something we can call the wireless squeeze. It's this huge set of challenges that engineers are up against when they try to roll out something as powerful and complex as 5G, especially in our busiest cities. What's so wild about this is how all these challenges just stack on top of each other. I mean, think about it. You've got thousands of people all crammed together, and every single one of them wants blazing fast speeds. The radio waves themselves are bouncing and scattering off every surface imaginable. Signals from different towers are actually getting in each other's way. And on top of all that, you have to install this dense network of what they call small cells, which is its own logistical nightmare. It's a puzzle on a whole other level. So how in the world do you solve a puzzle that complicated? Well, you don't guess. You build a virtual proving ground. Instead of the old, expensive, and super slow method of trial and error out in the real world, engineers now have a much smarter strategy: computational modeling. To put it simply, computational modeling is all about building the entire city and the wireless network inside a computer first. It becomes this perfect virtual lab where you can test literally everything: where to put the towers, what the signal strength will be, how to handle all the user demand, all without spending a single penny on real hardware. And this quote it nails the concept perfectly. Think about it, right? An architect would never, ever dream of building a skyscraper without a detailed blueprint. It's the exact same idea here. Network engineers now create a digital twin of their network, a perfect virtual copy, to design and totally perfect how all that information is going to flow through the air. So how do they actually turn the messy real world into a clean computer model? It really breaks down into these three core pieces. First, you have to define your main goal. That's the objective function. Are you trying to maximize speed or maybe minimize the number of dropped calls? Second, you identify all your levers and dials, the decision variables. Where can we put towers? What power levels should we use? And finally, you have to lay down the rules of the game, the constraints, things like your budget or, the simple laws of physics you can't break. Okay, so that's the theory, but let's see how this actually plays out in the real world. We're going to look at a case study of a major mobile network operator that was facing this exact problem, rolling out a brand new 5G network in a super dense city. And you're going to see how this modeling approach completely changed the game for them. I mean, just look at the difference here. On the left, that's the old way of doing things. It's basically expensive guesswork. It takes forever, and you never really know what you're going to get. But on the right, that's the new way. Instead of guessing, you're simulating. Instead of wasting money on rework, you're saving a ton. It basically turns network design from this risky gamble into a precise, predictable science. And these were the goals the operators set for themselves. And look, they weren't aiming for some tiny little improvement. They wanted a minimum of 100 megabits per second for almost every single user. And they wanted latency so low, under 10 milliseconds, that everything would feel completely instantaneous. Hitting these kinds of numbers, especially in a crowded city, that would be pretty much impossible without a perfect blueprint. So, after all the simulations, all the virtual tests, it was time to build the thing for real, the moment of truth. Did the digital blueprint actually work? Well, the payoff was nothing short of dramatic. First, let's talk about average download speed. The new 5G network, the one designed with the model, delivered a staggering 300% increase in throughput compared to the old 4G network. That is a massive leap in performance. Next up, latency. That annoying delay that causes lag in your video games or your video calls. The model-driven design slashed it by more than 50%. The network didn't just get faster, it got way more responsive. And what about that really tough goal, the one about delivering 100 megabits per second?
Well, the final measurements from the real world confirmed it. 95% of users were hitting that target speed, exactly as the model said they would. I mean, that is precision engineering.
This chart just lays it all out so clearly, doesn't it? You can see that huge jump in throughput and that massive drop in latency. The modeling didn't just lead to a few little tweaks here and there, it resulted in a total transformation of the user experience. And the craziest part, it was all predicted and perfected in the virtual world first.
So, what does this all mean for what's next? Because this story isn't really just about 5G. It's about how we're going to build our entire connected future.
And here's the key takeaway. The complexity of our world, it's only going up from here. Future things like 6G networks or the Internet of Things, with billions and billions of devices all talking to each other, are going to be literally impossible to design with the old methods. This model-first way of thinking isn't just an advantage anymore, it's an absolute necessity to handle that scale and make sure our future innovations actually work. So we'll leave you with this final thought. We're now at a point where our most important physical infrastructure, from our wireless networks to our smart cities, is being designed, tested, and perfected entirely in a virtual space before anyone even touches a piece of hardware. So the question is, what other incredibly complex challenges could we solve by building their blueprints in the digital world first? The possibilities are just endless.